In Chapter 19, we're going to be discussing one of my favorite topics in chemistry, which is chemical thermodynamics. It's really, really important to understanding how the universe works. And if you stick around through this chapter, you will find that I will reveal to you the secrets to the universe. So let's get started. To get us going in chemical thermodynamics, we're going to review something that you should have learned back in Chapter 5 in this textbook, which is called the First Law of Thermodynamics. And the first law of thermodynamics just tells us that energy cannot be created or destroyed. It's sometimes called the law of conservation of energy. We will find that this means that the total amount of energy in the universe is a constant, which is it's kind of a bold concept, but according to thermodynamics, that is true, that the total amount of energy in the universe is constant. What this means in terms of for practical purposes is that energy can be converted from one form to another, or energy can be transferred from our system into our surroundings or from our surroundings into our system. But we can't create or destroy energy out of nothing. And that is the basics of our first law of thermodynamics. The whole reason I mention that is that we need that as a starting point for thermodynamics. So now we're ready to talk about our first topic, which is spontaneous processes. I want you to look over here. Well, first we'll say a spontaneous process is just anything that will proceed without any outside intervention. And so I want you to look over here on the left. We've got two flasks, flask A and flask B. Flask A has a vacuum in it, so there's no gas, and flask B, of course, has a gas that is at 1 atmosphere. The two flasks are connected, but there is a stopcock in between. That stopcock is closed. You can tell it's closed because it's perpendicular. That stopcock is closed, which means that the gases can't move between the two flasks. Well, not surprisingly, if we open up that stopcock, the gases will start to move, and that we can the gases will spread out, and we will get half of an atmosphere in flask A and half an atmosphere in flask B. And that we'll find this is a completely spontaneous process. As long as the stopcock is open, this will happen. We'll find that processes like this one that are spontaneous in one direction are non-spontaneous in the reverse direction. Kind of as an analogy to this, if we have a ball that rolls down a hill, it will not spontaneously roll up the hill. Well, so the reverse process, where the gas on side A will spontaneously migrate back over and increase the pressure in flask B up to 1 atmosphere and create a vacuum in flask A, that's just not going to happen. That is a non-spontaneous process. Now, certainly individual molecules can go back and forth, but all of the gases going over, it's just not going to happen. Now, one thing, I want to mention actually two things here before we leave this particular page, and that is I don't want you to confuse spontaneous processes with fast processes. Technically, even with the stopcock closed, it would be spontaneous for the gas to flow from flask A or flask B to flask A. That would technically be a spontaneous process. The only problem is that we've got this stopcock in the way, and so we have a very high activation energy. So we can have reactions that should be spontaneous, but that can't happen because there is just too high of an activation barrier. So that's one thing that I want you to remember. The other thing is I don't want you to confuse non-spontaneous processes with impossible. So we don't expect all the gases to spontaneously flow over from A to B so that we get a vacuum in A and 1 atmosphere in B. Technically, that could happen but the probability of that happening is so low as to be laughable. In addition to that, we can force the gas to go back over by doing something like perhaps adding a pump that would pump the gas from flask A back over to flask B. So we can possibly reverse things, but it does take work to make that happen. Let's look at another spontaneous process. This one is a chemical reaction instead of just a physical process. And this is where iron is rusting. And so here we've got an iron nail that is sitting outside, and if it is exposed to water and oxygen, it will spontaneously rust. And so now we have a rusty nail right here. Well, here is the chemical process that is occurring. It's a chemical reaction. It's an oxidation-reduction reaction, which we're going to talk about more in the next chapter, but oxidation-reduction reaction. And so this is a spontaneous process. The reverse, where rust turns back into iron, is not a spontaneous process. So we shouldn't expect iron oxide, iron 3 oxide, to spontaneously convert into iron and oxygen. So you should not expect any rusty nails to suddenly become shiny new nails. That just doesn't happen. And so that brings us to problem number 8, which is the first problem on the in-class assignment. What I want you to do on number 8 is I want you to answer these before we go through them. So right now would be a good time to pause the video and give yourself a chance to answer these, and then here in a second, for me it'll just be a second, but you can come back and listen to my explanations. So let's look at each of these and determine if they are spontaneous. Spreading of a fragrance of perfume through a room. Well, I think everybody has experienced this at some point. This is definitely a spontaneous process. So I will just put yes, this is a spontaneous process. So since it's asking, is it spontaneous? The answer is yes. We've all experienced this, at a junior high dance, somebody puts on too much perfume or cologne or whatever, and they walk in the room, and that fragrance spreads throughout the room eventually. So let's look at the next one. Separating a mixture of N2 and O2 into two separate samples, one that is pure N2 and one that is pure O2. So if we've got a mixture of gases, we will find that they will not spontaneously separate. So this is definitely not a spontaneous process, so we will put no there. All right, this one we need to be careful and read the numbers here. The melting of ice at -10 degrees Celsius and 1 atmosphere. Well, ice we know will melt as long as the temperature is above 0 degrees Celsius, but at -10 we should not expect this to be spontaneous, so we're going to answer this with no. All right. D, the reaction of sodium metal and chlorine gas to form sodium chloride. Well, personally, I have seen this reaction. I have done this reaction. I know that this is a spontaneous process. However, if you're not sure, is this a spontaneous process, you can always look at the reverse and see, is that going to be spontaneous? So the reverse would be, well, sodium chloride breaking apart to form sodium metal and chlorine gas. Well, that is definitely not going to be a spontaneous process. That would be an impossible process to happen on its own. So if the reverse process seems ridiculous, then the forward process is probably spontaneous. Finally, the decomposition of liquid water into oxygen gas and hydrogen gas. Well, I think that would be very surprising if that happened. That is not a spontaneous process. So not a spontaneous process. All right, well, let's go back to the presentation, and we will look at the next thing, which is experimental factors that will affect spontaneity. And so one of the experimental factors that will affect spontaneity is temperature, and another one is pressure. In this case, we've got temperature, and so you'll see here, here we've got ice, which is H2O solid, and going to the right, it gets converted into H2O liquid. Well, we know that that will occur spontaneously at temperatures greater than 0 degrees Celsius. The reverse, we have to change the conditions for the reverse to occur. We would have to decrease the temperature below to turn water into ice. So we will find that this is spontaneous at one set of temperatures and non-spontaneous in another set of temperatures. So let's look at number 11 on the in-class assignment. And I've got this one here. Consider the vaporization of liquid water to steam at an atmosphere of, or at a pressure of 1 atmosphere. And I've written out the equation for this. This is, again, is not a chemical reaction, it's a process. So H2O liquid getting converted into H2O gas. Well, first of all, is this an endothermic process or an exothermic process? Recall, endothermic, delta H greater than 0, and for endothermic, that means heat has to flow from our surroundings into our system for it to occur. For exothermic, heat's going to flow from our system into the surroundings. Well, on this one, to make water, to convert water from liquid to the gas phase, we have to absorb energy from the surroundings. So this is going to be endothermic. So endothermic. We definitely would have to add heat to this to make this happen. In what temperature range is this a spontaneous process? Since it is at 1 atmosphere, we're going to use the normal boiling point of water at temperatures greater than that normal boiling point. So we'll find at temperatures greater than 100 degrees Celsius, this would be a spontaneous process. At what temperature range is it a non-spontaneous process? Well, don't overthink this. At temperatures less than 100 degrees Celsius. At what temperature are the two phases in equilibrium? Again, don't overthink this. This is at a temperature of 100 degrees Celsius. So that was a pretty easy problem, but I like to start with these kinds of problems so that you understand that, first of all, thermodynamics is not that hard. All right, some of the math gets a little tricky, but it's not that hard. And second of all, a lot of it is logical. So here we go. We're going back to our presentation, and we want to talk about reversible processes. So here I've got the book definition for reversible processes. They are processes are those that reverse direction whenever an infinitesimal change is made in some property of the system. Now that sounds a little bit vague, and the reason that that sounds vague is that it is vague. Okay, that is vague. And so let me give you an example of something that is reversible. And we're going to use these pictures to illustrate this. So these images represent a situation in which an infinitesimal amount of energy is going to flow from our system into our surroundings, and then that same amount of energy will flow from our surroundings back into our system. Well, infinitesimal means almost zero. It's just the smallest amount of energy that we can imagine, and so yeah, we could imagine that a little bit of heat would flow from our system to our surroundings, and that conversely, that little bit of heat could flow back from our surroundings into our system. Presumably, when this happened, the temperature of this would go down, and then maybe the temperature of our surroundings would be a little higher, so it would have to go back to its original condition. And so that is an example of a reversible process. Well, if you think about that process, it's interesting, but it's not a very exciting process. We're going to find reversible processes are mostly there to help us with the math. And I'll explain what I mean by that here in a little bit. So let's look at an irreversible process. This irreversible process, this is much like the two flasks that we had in at the very first slide, or the second slide, which is, here we've got a cylinder that has a piston in it, and there is a movable partition between these two halves of the cylinder. And on the left half, we've got a vacuum. On the right half, we've got some gas at some pressure. Well, we know that if we remove that partition, the gas is going to spread out. That's just how gases work. They spread out to fill whatever space is available. And so we could imagine doing the experiment again where we put the partition back and then remove that partition again. Well, could we imagine the gases just flowing back and going back to their original set of conditions? And the answer is no, because that's not how gases work. Gases always will spread out to fill whatever space is available. All right. We will find that the forward process is spontaneous and the reverse is non-spontaneous. And so that means that this is an irreversible process. It only happens in one direction. Now, I do want to point out that doesn't mean we can't get it back to its original condition. As the third picture implies, we certainly could do some work on this system and force that gas back over to the right side and then slip that partition back down, and that would be in essence reversing that reaction. But it's not happening by itself. In order to do that, we would have to do work on the system to get it back to its original condition. So again, irreversible doesn't mean you can't undo it. It just means that you have to do work to get it back. And so that's what we mean. We will find that there are many processes that are like this, that they're irreversible, but we can get it back to where it is. We just have to do some work, right? There are other processes that are irreversible and we can't get them back. We would have to go through a very elaborate sequence of events to get it back to its original condition. So next, in the next section, we're going to be talking about entropy. And entropy is one of the most important concepts in all of science. It is also one of the most poorly explained concepts in all of science. And so hopefully I can clarify the meaning behind entropy for you. I'm going to give you an analogy for entropy. It's not exactly the definition. I'll show you the definition here in a moment, but entropy is a pretty good measure of the tendency for energy to spread out or disperse, and thereby reducing its ability to accomplish work. We will find that one of the overwhelming driving forces in all of the universe is for energy to spread out. If you have something hot that is in a room temperature room, so let's say you've got something that you just pulled it off the oven and it is glowing hot. Well, if you set it down on something, you will find that it will cool down, and in doing that, heat is going to flow from that hot object into the surroundings, into the room. And that is, in doing that, we're going to find that the entropy of our system, which will include the room and the hot object, that entropy is going to increase for that system. Okay, and so what we want to do is we want to get a firm understanding of when does entropy change and what does that mean. So we will find that entropy is a state function. So entropy is a state function. State functions, as we learned with enthalpy, state functions are simply things, they are energy functions, where we just look at where did it start, where did it end, and that will tell us what the change in enthalpy is. And we will find that I'm sorry, not enthalpy, entropy. So that will tell us what the change in entropy is. We will find that enthalpy, as I mentioned, is a state function. There's one that I'm going to introduce later in this chapter that is called Gibbs free energy. It is also a state function. Things that are not state functions are going to include, are going to include heat and work. So, so we will find that entropy is a state function. So let me give you a quick definition of what entropy is. So if we have an isothermal reversible process, we'll find that the change in entropy is going to be equal to the heat that is transferred divided by the temperature at which that heat is transferred. And while that is a weird concept, it turns out it's really important. So this entropy concept is really, really important. If we've got an isothermal just means at a constant temperature. So if we have an isothermal phase change at constant pressure, then this is the equation we just had. So the change in entropy of our system is equal to Q reversible of our system divided by the temperature in Kelvin. And if it's at constant pressure, then Q reversible is going to be the enthalpy of our system. So delta S will equal delta H over delta T. And that is an important equation. We're going to look at a phase change on number 21. So here we're back to our in-class assignment. So this is number 21. So the normal boiling point of methanol. Well, let's just go ahead and write down what this process is. We've got CH3OH liquid, and that is getting converted into CH3OH gas. All right. So the normal boiling point is 64.7 degrees Celsius. That normal boiling point, that is at 1 atmosphere of pressure. And its molar enthalpy of vaporization, in other words, the enthalpy of this process, is 71.8 kilojoules per mole. Well, because it's positive, that tells us that that is an endothermic process. So this is an endothermic process, meaning heat has to flow into this system to make this happen. All right, so we want to write the equation, and the equation is actually just the thing that we just had up on the screen. So delta S of our system is equal to Q reversible divided by the temperature. That temperature does need to be in Kelvin. And because this is at constant pressure, we can also write that that is equal to delta H of our system. And I'm going to put delta H of vaporization because we're talking about the vaporization. But again, the reason that we can write delta H is because it's at constant pressure. If we were talking about constant volume, I would have to put a delta E here, and that would be a different kind of equation. Okay, so part B, calculate the value of delta S when 1 mole of this substance is vaporized at 64.7 degrees Celsius. So delta S here, and the first thing I'm going to do is we are going to multiply by that. Well, we're going to write down the value here. So it is 71.8 kilojoules, and that is kilojoules per mole. And we're going to divide that by the temperature, and our temperature is at 64.7, but we need to convert that temperature into Kelvin. So we'll do 64.7 plus 273.15. And that's going to give us 337.85. So 337.85. So I'm going to put that number in, 337.85 Kelvin. And then the next thing we're going to do is we're going to multiply this by 1.00 moles. And that will cancel out the moles, so we'll get our answer in kilojoules per Kelvin. So we'll do that number. So 71.8 divided by 337.85. And that gives us 0.2125, and we have 3 sig figs here, so we're going to call that 0.213 kilojoules per Kelvin. Now, most of the time when we're reporting values for entropy, we will put them in joules per Kelvin. So I'm going to go ahead and do that conversion real quick. It's just multiplying that number by 1,000, and so we'll have 213 joules per Kelvin. Now, you may be looking at that number thinking, okay, well, what does that mean? Well, that's a good question. We are going to answer that question in more detail later. Units of entropy are a little bit weird to think about. So, all right. Next, let's see, when methanol boils at its normal boiling point, does the entropy increase or decrease? Well, we just need to look at the sign here, and since it's positive, that means the entropy increases. All right. If we had done this and it had been negative, that would tell us that the entropy decreases. So that is how we solve that particular problem. All right. So far, we haven't had any really hard problems. Don't worry. We're going to get to more challenging stuff. So on this particular page, I'm going to show you 2 equations, and I don't want you to get too excited about these 2 equations. And the reason I don't want you to get too excited, well, the equations are great equations, but they are not part of this course. I am showing them to you to illustrate a point. So we can write or calculate what the entropy change for a system is if we have an isothermal expansion. Again, isothermal just means at constant temperature, and we let a gas expand. Well, let me look at the values here. So delta S of our system, so we're trying to calculate that, is equal to N, where N is the number of moles of our gas, R is our gas constant, and then natural log of V2 over V1, that is this component. If V2 is equal to V1, then that ratio is equal to 1, and the natural log of 1 is 0. So this is only an interesting equation when the volume changes. So this is only an interesting equation when the volume changes. If the volume 2 is greater than volume 1, then we're going to have a number greater than 1, and that means natural log of that number will be positive. If volume 2 was less than volume 1, let's say we compressed our reaction, in that case, if volume 2 was less than volume 1, then this would be a number less than 1, and natural log of a number less than 1 is going to be negative. So if the volume increases, the entropy will increase. And that is the whole reason I'm showing you this equation. I'm showing you a mathematical proof that if the volume increases, the entropy will increase. Well, this is an important concept we're going to see over and over in this chapter. If volume increases, entropy increases. We're going to look at this particular equation, which is very similar, but instead of being isothermal, this one is at constant volume, and it's the temperature that's changing. And so here we've got delta S of our system is equal to the number of moles times the heat capacity at constant volume times the natural log of T2 over T1. Well, much like I mentioned earlier, if T2, again, this does have to be in Kelvin, if T2 is greater than T1, this is a number greater than 1, and therefore this will be a positive value. If T2 is less than T1, in other words, the temperature goes down, then this will be a number less than 1. Natural log of a number less than 1 will be negative, and our delta S will be negative. So if the temperature increases, the entropy increases. All right, here's my disclaimer. These equations, while interesting, are not part of the learning objectives. They will not be on the test. I'm showing these to you to get these 2 points across. As volume increases, entropy increases. As temperature increases, entropy increases. So now we are ready to go to our last concept in this section, which is the second law of thermodynamics, one of the most important laws of any of the ones that we run into. And it tells us this: the entropy of the universe increases for spontaneous processes, and the entropy of the universe does not change for reversible processes. Okay, now we can write this as a mathematical, or actually a pair of mathematical equations. The entropy change in the universe is going to be equal to the entropy change of our system plus the entropy change of the surroundings. If we have a reversible process, then the entropy change in the universe does not change. In other words, delta S will be equal to 0. That's for reversible processes. For all the interesting processes, the ones that are fun and the ones that actually happen on large scales, those are irreversible processes. And in all of those, again, delta S, the universe, is the entropy of our system plus the surroundings, but that value is going to be greater than 0. What this tells us is that it's okay for the entropy of our system to go down. But if the entropy of our system goes down, that means the entropy in the surroundings has to go up by at least the same amount and a little bit more for the reaction to, or the process, to be spontaneous. That's what that equation tells us. So it is possible for entropy to go down in our system, but that means entropy in our surroundings goes up. We do this all the time, right? In the summer, we like to decrease the temperature in our house. And I told you just in the last page that if you increase the temperature, you increase the entropy. And if you decrease the temperature, that means you're also decreasing the entropy. So if you want to decrease the entropy in your house, turn on the air conditioner, and that will lower the temperature inside your house. But in doing so, you are going to increase the entropy outside. All right, that's how we can make that happen. All right, let's look at number 22. Number 22 is actually the information that is on this page. I'm going to show you what I have written down for 22, but it's exactly what is up here on this page. So here it is. Write a statement that expresses the second law. Well, the entropy of the universe increases for spontaneous processes, and the entropy of the universe does not change for reversible processes. So for reversible, delta S universe is 0, and for irreversible, delta S of the universe greater than 0. So I'm going to leave that there. This will be the end of our first video for chapter 19. Our second video, we're going to talk more about entropy.